Our next speaker will be Sharon Goldberg from Microsoft Research and Boston University. She'll be talking about how secure are secure interdomain routing protocols.
This work is very recent, very new. Joint work with my co-author Michael Shapira, who's in this room, Pete Humman, and Jennifer Rexford. So what we're doing in this work is we're going to be looking at various interdomain routing protocols that have been proposed. So these are the traditional interdomain routing protocols that most people are familiar with. If you're not familiar with, I'm going to go over the details of how they work. And what we're looking at is how effective they are at preventing a particular kind of attack. Okay, so I'll go into all the details of exactly what we're doing. Because this work is so new, I'm looking for feedback. So if you have comments on the model or what things are doing or where Nick Feimster is, he's coming soon. Okay, so so please don't hesitate to give comments on any of these issues. Okay.
Sharon, do you want us? Is it okay if we ask questions?
Yeah, please stop me. It's going to be interactive. And the other thing I want to say is that a lot of the slides from this talk were given at a talk at Microsoft last week, which was a general audience talk. So assuming zero knowledge about anything. So a lot of the stuff here will be known to you. If you know it, I'll just go through it quickly. Okay, so I'm not trying to talk down to anyone. It's just that I want to be clear, make sure we're all on the same page. And if it's something you already know, then we'll get to something more interesting soon enough.
And can you and all speakers today make sure to repeat the questions so that they go into your language? Sure. Thanks.
Okay. So here's what we did in this work. So as everyone here knows, internet routing is surprisingly insecure. We have all kinds of attacks that happen that really shouldn't happen. So when I give this general audience version of this talk, I talked about the YouTube prefix hijack, which was when Pakistan Telecom actually grabbed all the traffic for YouTube and sort of dropped it all because the interdomain routing system is so vulnerable to just impersonating destinations. So there's been a decade of research on this. Many, many different secure routing protocols have been proposed. What we wanted to do in this work was, rather than look at a new secure routing protocol, just to look at the basic functionalities of all these different routing protocols and see how effective they are at preventing attacks. So given that these secure routing protocols work perfectly and they're fully deployed and everything's great, if we're in that world, how effective are they going to be? Okay? So in terms of effectiveness, first of all, each one of these security protocols has different security properties. So secure BGP, secure origin BGP, origin authentication, filtering, all of these approaches have different security properties, which we'll talk about exactly what they are. So I want to understand, given that the security property holds and everyone in the network is using this protocol, which is a sort of fantasy world at this point, but if we live in this fantasy world, how well are these protocols going to prevent a traffic attraction attack? So I'll talk exactly about what that means. But I believe that this is sort of the most basic form of attack you can imagine on the interdomain routing system. And we can argue about whether or not people here agree that that's the case. Okay, so how we did this was, we didn't do this with just sort of a theoretical model. What we were trying to do here was use some real data. The data that we were going to use is a map of the internet. So we're taking both CADA and the Cyclops data from UCLA, basically give us a graph of the internet, so an AS level topology of the internet, that also includes the business relationships between the nodes, between the autonomous systems. So we're using that as our data. And what we're going to do is we're going to generate a sort of model of routing policies based on the Gow-Rexford conditions. So for those who are familiar with Gow-Rexford, good. If you're not, I'll tell you exactly what the model is. Yeah.
Were the business relationships assessed through like Jennifer's AS traceroute kind of tool, or was it actually provided from real contractual information?
Yeah. So how these data sets look is basically, so is it clear to people? So the question was, what do these data sets look like and how are they generated? So what they are basically AS level topologies of the internet like this. For instance, this is a subgraph from what you might see. So there would be autonomous systems and then the business relationships between them. So for instance, customer to provider relationships where the customer pays the provider, and peer-to-peer relationships where the peers don't pay each other. So this is sort of a settlement-free peering agreement where two networks are not actually charging each other for carrying each other's traffic. Okay, so that's basically what the input to our model is, to our analysis is. So the way that these graphs were generated was they basically inferred them. So they took routing data, so they took like route views and BGP messages, I don't even know, all different sources of data, and then they ran inference algorithms to determine what the business relationships are. So the business relationships are inferred, they're not the ground truth relationships because we don't know what they actually are. So I can't look at the entire internet and say what the business relationships are between nodes, so we just use inferred data for that, okay? So just to go back, So these are the data sets. We use 2 data sets, and I want to say from the beginning that we validated this. We actually ran these tests on both data sets, and the amazing thing was the trends that you uncover on these 2 data sets, which were generated in different ways, are actually exactly the same. It was amazing. So at least within the model that we're using, the inaccuracies in the data sets don't seem to matter that much, at least for the general trends we're uncovering. So I'll show you actually some, like 2 graphs generated from this data set and that data set, and they look, in terms of trends, about exactly the same. Okay, so what we're going to do is we're going to use this model of routing policies. The reason we use a model of routing policies is I want to simulate traffic flow on the internet in the interdomain routing setting. So everyone, people realize that routing in the internet is not shortest path routing. It's much more complicated. But we don't know what the routing policies that networks are using. So what we're going to do is we're going to use this model. We're going to assume this model throughout, and then determine the traffic flow based on this model and use this to make our assessments. Okay, is this clear? Okay, so I'll get into the details of everything we did right now. Okay, so I'm sure that everybody here knows how BGP works, but I want to talk about this so that people see the level of our modeling, okay? So first of all, I want to talk about the model of routing policies we used. We're assuming that there's 2 kinds of business relationships. Customer-provider relationships are when the customer pays the provider. So in this graph, just so we have the terminology right, whenever I have arrows pointing, that means that the customer is paying the provider. So money is flowing along these arrows, okay? Then we also have peer-to-peer relationships. And so in a peer-to-peer relationship, nobody's paying anyone. The traffic is just transiting here for free, okay? And so in this graph, I have 2 peer-to-peer relationships. And just to note, this is a subgraph that comes from the CADA data from November 20th, 2009. So these are actual nodes in the CADA graph. Okay, so what we're going to assume that nodes do in order to decide how they choose routes is we're going to assume that they first prefer cheaper paths, and then when they have 2 paths of equal cost, then they'll prefer the shorter one. Okay, that's the model we're going to use throughout this talk. Okay, so we'll see how that works as I go through the examples. And this is not, the gospel truth for what every single network on the internet does, but this is the model that we used here because we needed some way of determining how traffic would flow.
Current load, don't they consider that?
No. No, so in our model, we're not considering traffic engineering or load or anything like that. We're just saying, so if I have an option, for example, if this guy has an option between routing over a peer where he doesn't make any money or through a customer where he does make money, he'll prefer the customer. So actually, I say it right here. So prefer paths through a customer over paths through a peer over paths through a provider. Because these are the cheapest, no money, sorry, you make money, you don't make money, and here you pay. Okay. All right, so for how BGP works, we're going to use AS level view of BGP, so eBGP, that's all we're going to focus on in this talk. And so the level we're working at is just the autonomous system level. We'll think of each one of these autonomous systems, which by the way is a giant network, so this is Verizon's entire network. This is AS 702. Basically we're just going to look at routing at the AS layer. Okay? So BGP works by setting up paths to prefix separately. So what we're going to do is focus on a single destination because each BGP instance is focused on one prefix, so we're just going to look at one prefix for this example. Okay? So this is the destination that everyone in the world is trying to reach. We're trying to set up paths from all these autonomous systems to this destination. So the way BGP works is basically it has the AS that owns this IP prefix announce that basically this is called originating an IP prefix. He announces his name and then he says the prefix as well. And that's the BGP message that he sends to his neighbors. And so BGP is an AS level path vector protocol. So that means that when this guy wants to announce a path to the destination, he's going to say, this is my AS name. So this has some number. UPC, which is the name of the guy before him, and then the destination address. Okay, so routing will continue this way. This node 20984 is going to learn 2 different paths, one from Verizon, which is going to be 3 hops long, and it's going to be of the form Verizon UPC prefix, so this guy's name, that guy's name, and then the prefix. And he's going to have another path here that's 4 hops long through 43284. So in our model, we're going to assume that nodes prefer cheaper paths and then prefer shorter paths. So if we look at this guy, he's got 2 paths through providers. So our model doesn't say how much he pays on each edge because we don't have that data in the graph that we're using. So we just know that this is the way the money's flowing. So in this case, money's flowing, for both of these are both provider path. So he's just going to choose the shorter one. Okay? So he routes through Verizon. Is this clear? Simple? Okay. Next point is this is sort of, so if people are familiar with the notion of valley-free paths, this is what gives you valley-free paths, this next part of the model. So we're going to assume that this guy, 209.84, is only going to carry traffic, or sorry, every node in the network is only going to carry traffic if it earns him money. So if we look at 209.84, question I want to ask is 209.84 going to announce any paths back up to his provider over here, right? So a BGP announcement is basically like a commitment to carry traffic. So if a node makes a BGP announcement to its neighbor, it's basically saying to that neighbor, hey, if you'd like, you can send traffic to me, right? So the question is, would this guy send such an announcement? Would he export such an announcement to his neighbor? And if we look at the business relationships here, what we're going to assume in our model is that because he's both paying on this edge and paying on that edge, having traffic flowing through him like this actually doesn't earn him any money. And so he's not going to make such an announcement because it's going to lose money for him. Okay, does that make sense? No? If you missed this, this is important. So,
It's okay.
Okay, so basically the bottom line here is that the only time a network is going to actually carry transit traffic, which means traffic from one AS, so basically like this is transiting traffic. Anytime that's going to happen is if at least one of the neighbors is a customer. So this guy's a customer, this guy's making money, right? He's carrying traffic for his customer. Even though he doesn't make any money here, he gets money here, so he's happy, and he'll carry traffic. Yeah?
So do you also assume that you pay in both directions on receiving traffic and
No, you only pay in one direction. So
you won't pay, you'll only pay money because you're sending the traffic up to Verizon, but not because you're receiving traffic from 43 to 84, right? Well,
okay, so in this figure,
oh, sorry, yes, you're right.
Okay, so your question confused me a little bit, but in this figure, this guy is sending traffic to Verizon, and he's paying also to Verizon. But this is traffic that's going to this IP prefix. If there was an IP prefix here, then we'd set up a different instance of BGP, and traffic would be flowing this like down through this guy, right? Then he would be also paying Verizon, for instance, if Verizon was sending him traffic. If the prefix was here. So you're thinking of bidirectional traffic. This is sort of one-directional traffic. It's only all going to the prefix. So the traffic always, in this figure, because we only have one prefix, traffic flows in this direction.
Right, and my question was,
Yeah.
if 2984 actually did end up announcing that advertisement,
Yeah.
and 43284 ended up sending traffic through to 2984, it's not going to pay 43284, it's just going to pay Verizon.
It's going to pay both Verizon and 43284.
Because it's going to be sending traffic.
Yeah, because this guy's sending him traffic. The money doesn't care which direction the traffic is flowing. So yeah, if traffic was to flow like this, he would have to both pay there and pay there, which is really bad for him. So we're going to assume that he's not going to do that. And so if people have heard of valley-free paths in BGP, this is why they exist. This is a valley, and we believe that these things shouldn't happen, at least under normal behavior. Okay, so those are the main assumptions for the model we're going to use. Okay? Yes? No? You don't get which part's unclear?
Some of your notation, but I'll talk to you about it later.
Okay, yeah, I do want you, we should sit down and talk about that. Okay, so okay, this is the model of the routing that we're using in this research. Okay, so what we're going to do now is we're going to look at various different secure routing protocols. I'm sorry if I went too fast. I was assuming that a lot of people have seen this stuff before. So we're going to look at a bunch of different secure routing protocols. These are the different ones we're going to consider. I don't care about implementation in this talk. I only care about the security guarantee I get from these protocols. So we can talk about the implementation of these. There's many, many implementation issues that are very interesting and complicated. We don't deal with them here. All we do is assume that they work properly and everyone uses them. Okay, so we live in this fantasy world. We're going to look at these different protocols, see what kind of attacks are possible against them, and see how effective the adversary can be if it launches these attacks. Okay. So first of all, what attacks have I been talking about? So the attacks that we focused on in this paper, we call them traffic attraction attacks. So basically you have an attacker, so this guy can be our attacker, and he wants to attract the maximum number of networks to route through his own network. So in other words, he wants to convince the maximum number of other ASs to send traffic through his own AS. Right? So this guy will be happy if basically, instead of sending all the traffic destined for this particular IP prefix, we call this the victim, so all the traffic destined for the victim should flow through the attacker, or as much as possible. And we measure sort of volume in the number of ASs that do this. The reason we do that is because of the data we're using, right? So this is a bit of a circular argument, but the best way to measure that on the data we're using, where we have autonomous systems only, is just to count the number of those that are routing through the attacker. And so that's what we do. Okay? So, and we treat each autonomous system equally. So why is this a dangerous attack? So assuming that the traffic is unencrypted, once it flows through the attacker can eavesdrop on the traffic. Even if the traffic is encrypted, once it flows through the attacker can start tampering with it. Even if it's authenticated, it can drop it and stop it from arriving at the destination. So basically the bottom line is once the attacker gets the traffic through his own network, he controls it. And then he can do whatever he wants to it. And so that's why we're focusing on these attacks, because these seem to be the most dangerous attacks. And in fact, the person who was supposed to speak today during this slot, Tony Capella, has shown that these things are very feasible, even in a stealthy way. And if you read some of the press that he got for his attack, a lot of the press was saying this is the most dangerous attack we've seen on the internet. So it's kind of interesting to see that people believe that this is actually quite problematic. Okay. So anyway, this is the attack we're focusing on. Does that sound good? So we don't care about control plane, data plane mismatch. I don't care about anything. All I care about is making sure that the attacker gets traffic to route through his network.
So the attacker is a router, right?
Yeah, so the attacker you can think of as a router inside one of the autonomous systems.
But you just said before, you said you assume everybody follows the rules. So everybody but one, or everybody
exactly.
two?
Exactly,
You
good
assume
point. One single attacker inside one network, inside one autonomous system. Yeah, and you made a really good point. This attacker is a router. It could be a hijacked router. This attacker doesn't have the same motivations as the network itself might have, because this network generally are economically motivated. They have these business relationships. They have all these things that they like to do. This attacker's goal in life is to attract traffic. It doesn't care about anything else. Okay, so you can think of it sort of as a router that's been hijacked inside one of these networks. The view we're going to look at is basically that one of these networks is malicious, but you should think about it as a router being malicious. Okay, so this is the simplest form of attack for traffic attraction. So I'm not going to, for those who know about sub-prefix hijacks, I'm just going to ignore them for the purpose of this talk because they're so successful. So we're not even going to look at them, and there actually are ways to deal with them. So if we want to talk about sub-prefix hijacks, we'll talk about that later. So this particular attack is called a prefix hijack sometimes, and this is what it is. So we have our network UPC, and he's the one that owns the IP prefix. Okay? Then here's our attacker. He would like to get the traffic for this IP prefix. What he's going to do is he's going to say, actually, I'm 209.84, and the prefix is attached to me. Okay? So when we look at what Verizon is going to need to decide to do, if we look at the business relationships in this particular graph, we have that Verizon has a peering relationship with UPC, and it is a provider of the attacker. Right? So if he routes this way, he's actually going to be making money because that's his customer. And so what this guy is going to do, if he just does prefer customer, which is what his routers should be programmed to do, then he's actually going to route this way, right? Because he doesn't know where the prefix actually belongs. He sees these two announcements, this one is more attractive, and so he's going to route this way. Does that make sense? Yes? Okay. So similarly, if we continue through the network, we get to init 7. He's going to see this path here, which is a 2-hop path to the prefix. And he's going to see this path here, which is a 1-hop path to the prefix through UPC. He's actually going to route through the longer path. And the reason for that is because this is a customer path, and so he's going to make money if he routes this way. Okay? That follows from our assumption that nodes prefer customers. Make sense? Okay, so this is the simplest kind of prefix hijack. And if you run this attack over the whole network, so basically assuming that everyone behaves honestly except for this one attacker, and then it chooses their routes based on these announcements, we actually found that 62% of the internet will send their traffic to the attacker. So that the traffic will end up at the attacker. And in this particular example, this attacker only has two edges, so he's only connected to Verizon and this network 432.84. All this traffic is going to end up at the attacker, is never going to get to the destination. Okay, so this is like a black hole attack, basically. Okay, so this is just simple. Lots of people have looked at this. What we did is we ran simulations for this particular attack on BGP. Okay, but what we're going to do is we're going to look at what happens when you have certain security mechanisms in place and how effective they are at preventing this attack. Yeah.
That 62% was for 209.84 in particular?
Yeah, this particular example that I'm showing you here on the CADA graph from November 20th, 2009. So this particular instance, yeah. And I'm going to show you aggregate statistics later, but I picked this one graph just so that all the concepts are clear. Okay, so this attack is pretty ridiculous, right? Because we have this node here that's claiming to originate a prefix that it doesn't own. And this is something that we see happens a lot, usually due to misconfigurations. And everyone will agree that this is a security issue, right? Because IP prefixes are allocated to certain networks, and you shouldn't be originating a prefix that doesn't belong to your network, right? So this should not be happening. Okay? So to deal with this, we have a security mechanism called origin authentication. It has lots of different names. So Steve Belevin will probably know it by the name of ROAS. But he's not listening. Okay, so anyway, this mechanism does the following simple thing. We basically imagine we have some kind of secure database that maps IP prefixes to the networks that own them. Okay, that's all this mechanism is going to do. So in this particular example here, this database would store the information, this IP prefix, and UPC is the owner. Okay, so we imagine that this database exists, and now the attack that I showed you on the previous slide doesn't work anymore, right? Because before we had the attacker originating a prefix that he doesn't own, this. Now we had this database, this guy here, and both this guy and Verizon can check the database and see that this is an invalid announcement, and they'll ignore it, and they'll end up routing to the right place. So this attack doesn't work. Okay, but is there another attack that works? Right, so assume we have this database. Is there something the attacker can do? Okay. So what the attacker is going to do is he's going to actually, instead of claiming that he owns the prefix himself, he's just going to claim he's connected to the network that really owns the prefix. Okay? So now his attack is going to be, instead of announcing that he is the owner of the prefix, he's just going to announce that he's directly connected to UPC. Okay? And so if we look at what's going to happen here, again, Verizon has this choice, but this is still the customer path, which is still cheaper, so he's still going to use it. And on the same side, on the other side, init7 has now a 3-hop path to the prefix versus a 1-hop path. But again, this is a customer, this is a peer, so he's going to prefer the customer path, right? Okay, is that clear? Okay, so when you run the simulation on this, you see he gets 58% of the internet. So really, origin authentication for this particular example hasn't really hurt the attacker very much, right? Before he had 62% of the internet, now he's 58%. So nothing's really changed. Okay. All right. So the next, okay. So if we look at this attack or this example, I'm sorry.
What do you mean by directly connected?
So he's inventing an edge. He's pretending that he's actually connected to UPC because his announcement says 20984 UPC prefix, which is sort of like claiming that there's a path from here, like this.
No database for that?
There is no database for that in this particular security mechanism called origin authentication. So in the origin authentication mechanism, all you have is a mapping between IP addresses and their owner networks. You don't have a database actually saying what the edges in the internet look like. There is a mechanism that contains the edges of the internet. That's called secure origin BGP. I'm not going to talk about that right now, just because there's too many things. But if we look at this example, just like what you say, this is not true, right? That path is not really there. So what we'd like is we'd like to have a mechanism that prevents nodes from making up paths that are not there. Okay? And that mechanism has many names, but the original name for it is secure BGP. So this is from Steve Kent's paper from 1998. Or 97. So what secure BGP does is it has origin authentication. So we do have this mapping from IP addresses and the networks that own them. But we also have the ability to make sure that paths are really there in the network. So the way secure BGP works, most people probably know this, we have to have public keys. So we assume there's some kind of public key infrastructure. Okay, this is the original secure BGP. There's many, many versions of it. The bottom line is what security guarantee it gives us. But I just want to show you how it works. We're going to assume that there's each one of these nodes has public keys, so they now have the ability to digitally sign messages. Okay? And so what they're going to do now is, instead of just sending their messages, they're also going to sign their messages. So what UPC is going to do when it announces its connection to the prefix, it's going to say, here's the path I'm using, UPC prefix, and he's going to sign that with his key. Okay? And so now everyone who can go to the database, check out UPC's public key, and verify that this message really came from UPC. And so when we continue through, when Verizon sends his message, he's going to send the path that he's using, sign it with his Verizon key, and also include the message that came from UPC, which is signed with UPC's key. Okay? So now we have this sort of chained authentication where every node on the path authorizes that this is the path they're using. So to validate this path, this guy 20984 would verify that Verizon, that this signature is correct, and also that this subpath UPC prefix was authorized by UPC by verifying that this signature is correct and making sure that everything matches. And so now we can verify that every path that was announced is actually agreed upon by everyone on the path. Okay, so if we continue through, for instance, when he sees announcement over here, it's going to have 3 different digital signatures, one from 43284, one from init7, and one from UPC. So the orange key, the purple key, and the yellow key. Okay, so you'll have all these different signatures there. Okay, so this is where things start to get somewhat interesting. Yeah.
I just have a clarification.
Yeah.
And yes, maybe everybody does this, but I'm just asking.
Yeah.
The thing that's signed is not just the path that was announced, but also to whom that
Yes.
was announced,
Yeah.
right? That's
Yeah.
why the whole thing is
Yeah.
in
Yeah.
color? Okay.
Yeah. Okay, so there's a slight change to the protocol from what you would do in normal BGP. What UPC had to do here was it had to put init7's name in the path that it signed over here. So what this does is that if this wasn't here, right, so this whole thing is signed by UPC's key. So now you can sort of verify that this entire subpath was over here, right? And then you can verify that this entire subpath here was in the previous attestation, right? And this entire subpath was in this attestation. So you actually need this for the protocol to be secure, right? Because if this is not here, you can do path shortening attacks, right? So what would happen is if this wasn't here, then, for example, 43284 could just use this yellow attestation and then get rid of this, and it would be able to get away with that. Okay. So for those who missed that, that's okay. Bottom line is you need this message structure in order for this to be secure. Okay. So anyway, this is not crucial for the rest of the talk. The point is that with secure BGP, you can only announce paths that were announced to you. Okay. So the question is, what can our attacker still do? Right? So he can't lie about paths. He can't claim he's connected to prefixes that he's not connected to. But what he can do is he can basically use the same kind of strategy we were talking about before. He's going to announce the shortest path he can get away with. In other words, the shortest path that the routing protocol doesn't flag as invalid to as many neighbors as possible. Okay, that's the strategy that he's going to use. So in this case, the shortest path that this guy has available to him is the one through Verizon, right? He's got 2 paths, one of these through 43284, and then one through Verizon. This one's shorter because it's 2 hops. So let's say he grabs that path and he announces it, right? And he announces it using secure BGP properly, which means he's going to, sign the message properly with his own key, include the previous message in the message that he sends. So everything looks correct. Everything is valid here. He hasn't cheated in any way, right? And now, does that make sense, what he's doing here? So he's just announcing a path. And now what this guy's going to do, 43284, he has to make a choice. He has a choice between routing through init7 and routing through 20984. So again, we look at the business relationships. On this path, he gets paid. On this path, he has to pay. So what's he going to do? Even though this path is longer, he's actually going to route this way. Okay, that's assuming that he is just preferring customers. And similarly, what this guy's going to do, he has the path to the legitimate prefix, and then he also has a much longer path that goes all the way down through here. But again, he prefers customers, and so he's going to route downwards. Okay? And that's because he prefers customers. So he just assumes that prefer customer, this route is valid, and he's going to use it. And so here's what happens when you run the simulation over the whole graph. 16% of the internet is going to be routing through our attacker node. This isn't quite an attack because he hasn't made up any paths, but it's certainly a way of getting traffic to go through your network. Right? So,
And that's for a node that's a customer node.
yeah, so what happened here was that when we get to the decision, right, the attacker is going to announce a path. He's going to sort of create a valley, right? He's going to announce a path to this guy. Because he's the customer, it's going to be preferred, and he's going to route through it. Similarly here, he's got a choice between a short path through a peer or a longer path through a customer. If he does prefer customer, which is what he's doing in our model, then he's going to route through the customer, even though the path is longer. Okay?
So this is highly sensitive to where he is in the network.
Yeah, so the attacker's success is highly sensitive to his position in the network. Good, and we're going to talk about that actually as well later on. So that's the setting that we're considering. Yeah.
Is this an attack because? Oh, sorry, I didn't see that you had
Yeah,
this
yeah.
at the bottom of your. Okay.
Yeah. So why is this attack? So it's unclear if this is an attack or if this is a manipulation or what do you want to call this. The bottom line is though, if you run the simulation, 16% of the network is routing through this guy, and that's his goal in life, is to attract traffic. So he's been successful. Okay. So whether or not you want to call this an attack, it's definitely a way to attract traffic, and I want to talk more about that in a second. But this is sort of the interesting technical part of this work that I wanted to talk about. In all of the works I've seen on attacks on BGP, what people assume is that nodes want to do path shortening attacks. Okay, that the right thing for a node to do is try to announce the shortest path he can possibly announce. Okay, and here's the reason that people think that that's the optimal attack, and in fact, that's what we thought was the optimal attack. So if we remember my model of routing policies, we assume that nodes are going to prefer the cheaper path, and then if they have sort of two paths of equal cost, in other words, where the money's flowing in the same direction, they'll prefer the shorter one. Okay? So if you have two customer paths, you prefer the shorter customer path. If you have two peer paths, you prefer the shorter peer path. If you have a peer and a customer, you'll always prefer the customer. Okay? So basically, why would an attacker think that announcing the shortest path is a smart thing to do? Well, he can't lie about his business relationships with his neighbors, right? So your decisions are based on, first of all, what the business relationship is with your direct neighbor, so that this guy is deciding based on his business relationship. So he can't lie about his business relationships, right? So the only thing he can really lie about, because nodes know what their business relationships are, there's a contract between these networks and the networks know what the contract says, right? So they're going to already know what their preferences are going to be based on the direction of the flow of money, right? So what can they lie about? The attacker cannot lie about the business relationship, but he can lie about the path that he's using, the length of the path that he's using. And so that's why people have been assuming that things like prefix hijacks, when you're originating prefix that you don't actually own, would be the strongest possible attack. So the most effective kind of attack. Does that make sense? Why that would be to be the right attack? The other thing that people tend to assume is that you would want to announce the paths to as many neighbors as possible, right? Because every time you announce a path to a neighbor, it's like a commitment to carry their traffic, right? So if I want to attract as much traffic as I can, I should announce to as many people as I can, right? If I announce to fewer people should route through me. Okay? So this is the reason that we thought that this was the actual best attack on these networks, but it's not. So we are able to show that, first of all, announcing the shortest path is not always optimal. Sometimes announcing longer paths is better than announcing shorter paths in terms of just raw attracting traffic to your network. The other thing that we were able to show is that sometimes announcing to fewer neighbors is better than announcing to more. Okay, so I'll show you graphs where you announce to the maximum number of neighbors and then you announce to less than the maximum number of neighbors and you get more traffic. So what turns out to be like intelligent attack strategies that we've looked at on different example networks tend to look very strange. In fact, we have examples that show from the data that we used that the prefix hijack that everyone considers, which is just sort of like announcing you're owning a prefix that you don't own, there are actually more clever attacks that you can do by announcing longer paths, which is very strange. So bottom line is, once you see how strange these attack strategies are, it's not very surprising that we can show that it's NP hard to find the optimal attack strategy. Okay, so I'm not going to show you the proof, but it's a reduction to independent set. But we actually are able to show that. So what does this mean for us when we're trying to do research in this area? Okay, so if we're trying to understand how bad attacks can be on a network, what this result is telling us, yeah.
You say it's NP hard, that typically means worst case. What about heuristic?
Yeah. Yeah, so right, so in the worst case, it is hard. What we can show is that this is a good heuristic. This is a good heuristic. It's not the optimal, okay? So what I can show you is examples where this heuristic is actually not the best thing. There is a better strategy that you can use. But when we did the simulations, we didn't actually try every possible strategy that the attacker could do because there are many of them, okay? Does that make sense, what I'm saying here? So it turns out that this is actually a pretty decent heuristic, but it's not the best attack always. I'm going to show you examples specifically where it's not the best attack. But what this means for us when we're doing this analysis, if we want to do sort of an aggregate look at how effective these attacks are, we were not simulating the best attack. We were simulating one possible attack. There could be worse attacks. So all the results we get are going to underestimate the amount of damage that could happen.
And
Yeah.
maybe this is jumping ahead.
Yeah.
If you call the listed strategy here like the smart attack strategy,
Yeah.
and you can refer to it as a heuristic as you did.
Yeah.
Through simulation, is there some other similar heuristic that turns out to be better, like on average all the time? You know, something like that through simulation?
Yeah, I mean, one thing you could do in simulation is, okay, can I defer that to later?
Of course. That's why.
Yeah, maybe it's better to look at some examples first, and then we can see what different bad attack strategies would look like. Okay. All right. So anyway, this is sort of something very interesting because most of research that we've looked at, that I've seen at least, has assumed that this has been the worst thing that you can do, and it's not. Okay. I'm going to show you now why announcing longer paths can be better. Okay, and this is going to be the same example we've been talking about this time. Okay, so here's our attacker. Now remember that before, what he was doing, we're in the world of secure BGP now, so everyone has secure BGP. So before, what the attacker was doing was he was announcing a path like this. Right, this was his shorter 2-hop path. Okay, what I'm going to have him do now is announce his longer 3-hop path. Same thing as before. So now, instead of claiming to 432.84 that he was routing through Verizon, he's going to claim to Verizon that he's routing through 432.84. Okay, so he forms his secure BGP announcement correctly, as usual. Right, everything is signed, everything is correct. And Verizon is going to route through him for the usual reason. Right, this guy is a customer. This is a peer. Hi, Nick. So Verizon is going to prefer this path, even though it's longer. Okay? It's the same deal as before. So the reason I'm showing you this is because when we ran the simulation, it turns out he attracts 56% of the internet. And this should be impressive to you because when we did the prefix hijack, he attracts 62% of the internet. So it's almost as effective as the normal prefix hijack. So with the shorter path, he attracted only 16%. With the most sort of malicious attack that everyone would agree is malicious, he attracts 62%. And with secure BGP, he can still get almost the same amount of traffic going through his network just by announcing this path here, which is a legitimate path. Okay? Any ideas why this works? Yeah, okay, so some people see it, right? So Verizon is a huge network. Right? So with the previous attack, he was drawing traffic from this guy with a shorter path. But in this attack, by drawing traffic from this guy and sending his traffic through Verizon, he wasn't getting the traffic from Verizon. So by doing this attack, he gets the traffic from Verizon, which is a lot more. A lot more networks use Verizon, and so they're routing through the attacker, and he's been as effective as before. So what this basically shows you is the reason that this attacker was so effective at the beginning was because he got Verizon to route through him. And that's what he's doing here, so he's happy. Okay? So the bottom line is this is supposed to show you that this is a lot more complicated than you'd think. Okay, the other thing it should show you is that the who you make the announcement to is as important as the announcement that you make. Right, so in this example, what mattered was that Verizon was the one sending the traffic to the attacker and not the fact that the path was long. Okay, so okay. So now this question came up before, why is this an attack? Right, so why is this an attack? So I don't know that this is an attack, and actually I'm curious what people think about this. Yeah.
I was just going to add,
yeah.
Since you brought up something about
Yeah.
this aspect, just quickly, like, given the earlier idea that you said if this wasn't an attacker, then this is like a valley. This
Yeah.
path is a valley.
Yeah.
Is that one reason why you could call
Yeah,
it
that's why that's why I'm going there. Yeah. Yeah, that's where I'm going with this. Yeah.
So one thing to keep in mind from an operations perspective is that if Verizon has a customer relationship with 209.84, he will generally install route filters that will drop any advertisements that come from 209.84 that weren't propitiated by 209.84.
Good. Great. Good. Okay. That's the next thing we're going to evaluate. Okay. So I'm going to evaluate the heuristic solution that operators use today, which is route filters. I called it defensive filtering. I don't know what people call it. Egress filtering? Ingress filtering? Okay, let's call them ingress filtering. It doesn't matter. Bottom line is these access control lists, basically, that say that you're announcing a prefix you should be announcing. So, okay, so we'll go to there in a second. Bottom line is, with this, what I want to say is that this attacker can sort of get a lot of traffic through him if nodes blindly prefer customer, which we assumed for the purpose of this simulation, because we wanted to look at I wanted to sort of be very clear on what each different protocol was doing. So let's assume secure BGP with no filtering, origin authentication with no filtering, BGP with no filtering, and then all of them with filtering, which is what we'll do later. So this guy here in this network is a stub. A stub has no customers, right? So there's actually no reason for a stub to carry traffic through his own network because he's going to be losing money no matter what, right? If a stub has no one who pays him to carry traffic, then there's no reason for him to carry traffic through himself. So when we say carry traffic or transit traffic, it means that this guy is carrying traffic from one network to another. In this particular example, this guy's paying on both edges, so if he was rational, he wouldn't really do this, right? Unless something very strange was happening in this network, like some backup path or something was in place here. Normally, this shouldn't happen, okay? And so, what I want to evaluate now is this egress filtering, defensive filtering, whatever you want to call it. And so that's what this mechanism is. So what we want to assume now is that a provider here has a list of the IP prefixes that its stubs are supposed to be connected to. So imagine that a provider, when a stub connects to it, when a customer says to that customer, please give me a list of the IP addresses you plan to originate. Right? And in practice, a lot of networks do this. So I know that UUNet does this. I don't know what UUNet is called now, I forget. But anyway, people do this. So they keep a list of, this is this particular stub, and these are the addresses that it's supposed to have. And anything that's not within that set of addresses or is more than one hop long, then they'll ignore, right? So what would have happened in this example is that Verizon would have said, wait a minute, I'm going to check my list of addresses, of IP prefixes. This particular prefix is not in the list for this stub, and so I'm going to ignore this announcement. Right? And then Verizon would have routed through UPC. Does that make sense? So what we're doing is instead of having sort of like a global routing protocol, what we're counting on is counting on every provider to make sure that it has a list of what its stubs are supposed to be originating. Okay? And if we had such a thing in place for every network in the internet, then all attacks by stubs are eliminated, if such a thing was in place. Okay? So, yeah.
If you haven't already anticipated that, if you anticipate that you're going to launch an attack against a prefix when you register with your provider, does that?
That's a huge problem. Yeah, so how do you actually implement such a magical thing properly at every provider in the internet is a huge question, right? So like I said, we didn't focus on implementation in this work. We just wanted to see that if we had these different security properties, how effective would they be? This is actually very hard to do in practice. I'm going to talk a little bit about why it's hard to do this always. So one thing that Aaron brought up was, what happens if this guy was like, I'm going to always try to hijack this prefix, so when I register with my provider, I'm going to say to the provider, actually, I own this particular prefix. And so now I can hijack it all I want, right? There's not really a good way to stop that today. So what we just assumed was that we assumed that defensive filtering was implemented perfectly, it all works well, and how effective is it going to be? How you go about implementing that is another problem. Okay? Clear? Yes. Okay. So I went over the different attacks, and now what I want to do is talk about some of the results, okay? So what I'm simulating here is the smart attack. So remember, the smart attack is where you announce your shortest path to as many neighbors as possible. So like I said before, this is going to underestimate the damage, right? Let's keep that in mind, but just for now, let's look at what the results say. These yellow curves assume no defensive filtering. So assuming that operators were completely not having these lists in place, blocking off prefixes that shouldn't be originated by their customers. Let's assume they just believe everything that's told to them. And by the way, this sometimes happens when people don't implement filtering properly, and a lot of people don't implement filtering properly, which is why we do see prefix hijacks, right? So in this world, it's just plain BGP. Nobody has their filters configured at all. And this is the probability of attack. So what I'm showing in this graph is, let's say that an attacker is successful if he gets 10% of the internet to route through him. Okay? Just I picked a number arbitrarily. Turns out that 88% of attackers are going to be successful, right? So basically what I'm doing is I'm choosing attackers and victims at random and then simulating the attack and seeing how many nodes route through the attacker. If more than 10% of the internet does, then the attacker's successful. Okay, so for 88% of them, attackers are successful. If we put secure BGP in place, so where we have signed announcements, so cryptographically signed announcements, that number drops down to about 12%. Okay? But what's interesting now is suppose I lived in a world without secure BGP at all. We're just in the world of BGP, and we assume that every single operator does defensive filtering properly. This is what we see. So we see actually about 14% of attackers are going to be successful, okay, over the whole internet. And so what's very interesting here to me, at least, is that the defensive filtering level of success is about comparable to the secure BGP level of success, right? And this is what happens if you have both. It drops down to about 2%. Okay, does this make sense? So what you're seeing here really is only attacks by non-stubs, and by non-stubs that are announcing paths that are really there in the network. So what they're really doing here is basically they're violating valley freeness, right? So there's some sort of non-stubs that are actually able to hijack traffic by broadcasting announcements more widely than they normally would. The nice thing about this is that, at least in the data that we have, we found that 85% of the internet is a stub. Okay, 85% of ASs in the internet are stubs. So if we completely eliminate attacks by stubs by doing defensive filtering properly, this is a hard line for these purple bars. These purple bars cannot go above this line because 85% of nodes cannot attack. But what we do know is that the attack strategy that I simulated here for many, many cases could actually underestimate the amount of damage. Just like I showed when I announced this shorter path, I could get more traffic by announcing a longer path. So these yellow bars could be a little higher. And so what this is suggesting is that the defensive filtering heuristic is actually comparably effective to the secure BGP heuristic. Okay? Not heuristic, to the protocol. Right? And the interesting thing is that this is a cryptographic protocol, and this is sort of an access control distributed protocol. Okay? Does that make sense? Okay. So just in case you were wondering why I was doing 10%, that graph is really just this line here. So this was BGP at around 88%. This one was origin authentication. These bunch of lines here, these blue ones, these light blue ones, these are secure BGP. And these squares are the defensive filtering curves. So this is just basically this curved scaled down, removing all the stubs. That's this one scaled down is over here. Okay? And this is, you can see what happens if nodes behave honestly. So if we have no attacker, everyone follows the routing policies. Every single node in the network follows the routing policies. This is the number of nodes routing through the attacker. Okay, so just it's a little confusing. This is at least 10% of nodes in the internet routing through the attacker. That's what this line is. Right, so if we look over here, I could draw this line here and generate the same graph I showed you for 40% of the nodes routing through the attacker. Okay, so this is basically what the data is showing you. And these lines are on top of each other, which sort of suggests that secure BGP, secure origin BGP, and plain BGP with defensive filtering are about comparable. Yeah?
How do you get these numbers without knowing what AS's local preferences are?
Okay, so you missed the first part of the talk. So I'm using a model of routing policies. The model is the...
You're using like our expert?
Yeah.
But we know that that isn't really like that. I mean,
yeah.
It's not that common, so...
Well, I don't think it's... I think it is common.
I mean, there are many, many exceptions to that, right?
Yeah, there are exceptions to that, but the problem is I don't know what those exceptions are.
So, I mean, how much can we trust the actual numbers, like 10% that you're reporting? Like
I don't think, no, okay, so I don't think you can trust the actual numbers that I'm recording. What I can, here's what I can, so let me answer that question slowly. So the question was, how much can we trust these actual results? Okay, so here's what you can trust about these results. This is this graph generated from the CADA data. So I used two different input data sets. This is the CADA input data set. This is the Cyclops input data set. Okay, you can see these graphs. The trends are just about the same. Okay, so the bottom line is that these lines are sort of on top of each other, these three lines. The BGP line is above the origin authentication line. These three lines are together, and then the honest case is down here. This is for two different data sets. The data sets were generated independently. Okay, so at least between data sets, we have consistency, which made me very happy because I was very concerned about the accuracy of the data sets, and there's huge amounts of concerns about that. In fact, the data set that I used wasn't even just the UCLA data. So those people who follow these things, this is the UCLA data plus Walter Willinger's latest IXP data set. So there's a whole bunch of extra peering edges in this data that Walter Willinger and their collaborators found, reported about 2 months ago at IMC. So it's sort of like the state-of-the-art data set right here. And it doesn't seem to matter very much, right? So that we can trust. The things that are questionable about this model is the fact that, about these results, is the fact that I use a model of routing policies, right? So I don't know what actual routing policies used for real in the internet are. I'm just using this model because I don't have the information about what the routing policies are, Okay, so this is basically, in my opinion, the best I can do. I'm very happy to take suggestions on better models of routing policies. But what I need to know is I need to know how nodes are making their routing decisions and simulate flow of traffic on the internet. And so this is sort of the best I can do. If there are better models out there, I would love to know what they are. If there's more data out there, then I would love to have it. But this is what we did with the data that we had. Okay. So again, I don't think you can trust the actual numbers, but the fact that these curves are sort of on top of each other, that they're separated with a certain amount, that things are comparable, that's sort of the level of things that I want to demonstrate with these results. Is that, yeah?
Did you look at all at if you sort of partially implement the defensive filtering, like at the
No, we didn't.
percentage? Because it seems like since the way you were the attacker was doing better was by attracting traffic from the big providers.
Yeah.
You know, with even just sort of the big serious providers.
Yeah, no, we didn't do that. We could probably do that. That's actually probably pretty easy to do. So I would just have all the big providers do the defensive filtering and see what happens. No, yeah, that would.
With big providers doing defensive filtering is a lot of the stuff is indirect through their downstream ISPs.
Yeah, exactly. So we would have to assume that they could only filter their direct customers, which would limit the amount of filtering that they could do.
That's my concern about.
Yeah.
I think it would be interesting to look at because I think if you go back to that bar chart, if you look at this, it says that SBGP and the defensive filtering are about the same. Defensive filtering is cheaper. The question is, what happens if the big providers are doing SBGP, some percentage of origins, versus how much, who is doing, who has to do the defensive filtering?
Yeah. So this is like assuming that it's perfect
Right.
throughout the whole internet, which is, yeah.
So I would like to see that. I suspect that will give, my guess is it will give more of an edge to SBGP.
Okay, yeah, I can definitely get those numbers. That's not even, I have the data right now, actually. I could probably even get that in the next couple of days. Yeah, Nick?
I think this is interesting. Basically equivalent to SBGP. I mean, this sort of begs the question of why one is hard and what you might do to make one or the other possible. I mean, I guess we know defensive filtering is hard because it's difficult to keep registries up to date. It's difficult to sort of track ownership of prefixes. SBGP is hard for a different set of reasons. So which is easier to fix?
Yeah, that's...
Of course, I guess if you could get both, that'd be great, but...
Then we'd still be here. Yeah, so I think what we were trying to do with this work was just to raise these issues. I don't know how to answer these questions. I have some ideas, but we were just trying to see. So I guess one thing that we should be doing is running defensive filtering just on the large networks, see how effective that would be, because I'm assuming that every single network, even a little stupid network somewhere that has 2 customers, is also running defensive filtering, at least with these numbers. Okay, so I wanted to show one more graph before I finish. What?
Another sort of question about the sort of combining defensive filtering, SBGP. So defensive filtering's hard at the core. SBGP is hard at the edge. If you thought about doing something like, how about defensive filtering very close to the edge, and then upstream's basically signed to at least say, well, I'm not sure about, I can't sign on behalf of these advertisements, but at least I know filtering is going on downstream. I'm willing to vouch for that. Could you use?
Yeah, so that's a really good idea. It's a little tricky because if the edges are not signing, then you don't have signed origins, and so you can't build up the chain of trust for the secure BGP announcement if most of the destinations are at the edges. So it's unclear what secure BGP is doing, and in fact, Steve has a really nice attack that shows you what happens when you just blindly partially sign paths that we can talk about after. It's very cool.
Does knowing about defensive filtering from the edge basically serve as a proxy for a signature at some
Maybe, yeah.
That's kind of
Yeah.
That's kind of what I'm asking. Is like, can you proxy to say like, okay,
maybe.
well,
Yeah.
almost like taking a page from the Pathlet idea, right? To say like, okay, well,
question to ask, right?
here's a sequence of ASs that I'm reasonably sure is okay because the downstream guys have at least
I mean, the risk that you break defensive filtering then is, of course, very high compared to the risk that you break some signed thing. But, I mean, if you had some knowledge that would allow you to proxy that decision, maybe it would make a difference. And it's a good question to ask.
Yeah. So, okay, so quickly before I finish, I just want to show one more piece of data which I think is interesting, and some people find it surprising. What I'm showing here is the effectiveness of different attacker types. Okay, this is assuming that the attacker is not a stub, which means he has at least one customer. Okay, this is the attacker has at least 25 customers, and this is the attacker has 250 customers. So you can think of this as like a tier 1, a tier 2. These guys are kind of both tier 2s, but this is a bigger tier 2. It has at least 25 customers. This might be like some small network with one customer or something. Okay, so what I'm showing here is the success of the attack. So these green curves are the 25 customers. These are actually the most successful ones. So for example, if we say an attacker is successful if he gets 20% of the internet to route through him, right? Then I just draw a line up here. This green curve is higher than these other curves, which means that more fractions of attackers are going to be successful. Okay? So what this graph, does that make sense? It's a little hard to read this graph, but basically the higher curve means more successful attackers.
And Sharon, the green line, greater than 25 customers, it's greater than 25 but less than 250?
No, it's just greater than 25.
Okay.
But I actually did, I ran both, so they look the same. Okay. So you can just, the trends are about the same. Because there's so few greater than 250, there's like 34 of them or something, so it's not very high. The bottom line is that these guys, the guys who are about the tier 2s, who have a significant number of customers but not the most customers, are the most effective attackers. They're more effective than non-stubs, but they're actually even more effective than the tier 1s. Okay? So you'd think that tier 1s could attract the most amount of traffic because they're central to the network. In our model, at least with the data we use, that's not the case, and I'll tell you why. The reason is because the tier 1s don't have any providers, which means that they're nobody's customers. Okay? And since nodes prefer customer paths, they don't have that extra sort of having a lot of people prefer them because they are their customers. Right? So when we looked at the example that I showed, our attacker was a customer of a lot of networks, and so he was able to draw traffic through himself even though the paths were long. Right? When we look at tier 1s, they don't have any providers, so there's nobody who's going to prefer them blindly even if their paths are long. And so it turns out that the tier 2s who have a lot of providers, so you can think of like a tier 2 sitting here, and it has 2 tier 1s, it announces, this is a completely useless marker. You have here a tier 2, and here are 2 tier 1s. These are both its providers. It's going to announce some path, and the tier 1s are going to prefer it. And so a lot of traffic is going to end up flowing through it. Yeah. Yeah.
These numbers are on vanilla BGP, no filtering, no...
Oh yeah, sorry. Yeah, this was vanilla BGP, but you could do this for every different one, like origin authentication, filtering, whatever, and it always comes out with this guy on top. Yeah.
Does attracting imply that they didn't have the traffic originally? And
No.
they do?
No, it's just how much traffic goes through the... Yeah.
Okay. So
Yeah.
like you couldn't say that tier 1s get a lot of traffic anyway, so that's why there's not that much of a change. That doesn't
No,
play
no,
into
no.
the numbers.
No, this is just the raw numbers. Yeah. Yep.
Have you thought about, I mean, I know I missed the beginning motivation about attraction, but I've seen some of your motivation. I'm wondering if you thought about other kinds of things other reasons why, sort of a staged attack where, as an AS, like I want to attract more traffic to basically, make myself more attractive for peering, and then in doing so, I get more connections, and then that gives me more power to mount some other attacks.
That's very
More of
clever.
like a longer range
that's
attack.
that's an interesting idea. No, we didn't do that. We were just looking at short term, how much traffic can I get right now? But yeah, that would definitely be something that you could do. Like you could violate value freeness, for instance, to get more traffic to yourself, to maybe ramp yourself up to being someone's provider, and then your position in the network has basically changed and you become more powerful.
Yeah, Norton in his playbook talks about these like traffic manipulation kind of attacks. So that's where this kind of came to mind.
Okay. Who is that? Norton?
Bill Norton, like he has this peering playbook where he talks about games ASs can play to try to make themselves look more attractive as peers.
Okay, that's good. I'll look at
So
that.
it seems like another motivation.
Okay.
Formerly, yeah.
Okay, no, I haven't seen that. That's good. That's interesting. So I was just looking at attacks, just how much I can get right. Okay, so that's the last chart I wanted to say. So here are the conclusions I think from this work. First of all, who you announce paths to is as important as the path announce. So sometimes, there's been this focus on making sure that people don't lie or shorten paths artificially in order to attract more traffic to themselves. Something that I think is very clear from this work is that that's not the only way to attract traffic. You can sort of announce more broadly or more cleverly and get sort of as much traffic as you would have done by announcing shorter paths, at least in certain cases. Okay, so these are all things that we need to think about. And the majority of secure routing protocols have focused on, with the exception of defensive filtering, the majority of the secure routing protocols we look at are focusing on lying about paths. Okay, and so what this work is saying that we need to think more broadly about also how nodes export their paths. Okay. From a more theoretical perspective, what this work showed is that finding the optimal traffic attraction attack is hard, and that announcing shortest paths is not always optimal, contrary to what most of the works have assumed. And this is not just a theoretical result. I showed you real examples from the data set that I had that this could happen. Exporting to all neighbors is not always optimal. I have another example, which I don't think I'll have time to show, but it's also very cool, where a node will announce to less neighbors and attract more traffic that way. And so this makes it very hard to actually compare across protocols, right? We can compare for a particular attack, but it's very hard to compare for all attacks, which is what we would like to do ideally. Yeah, and so defensive filtering is pretty important. Okay, and so last thing I wanted to talk about was just how do we actually do defensive filtering properly, right? So today we have it in place, but it's very optimistic, right? What we're assuming is that we assume that nodes somehow know what prefixes. So what providers, this guy here, Verizon, will know what prefixes that its customer is supposed to have. And if it doesn't, if it announces something that's not on this list, then you should ignore the announcement. So that means that we have to assume that this guy is going to do this properly. Okay, so if we want to believe that every node in the network is doing defensive filtering, every single node has to do it individually, right? And so basically, it's sort of an altruistic thing. I'm going to do defensive filtering, protect the rest of the internet from my customers, right? Also, so maintaining the list is hard. But here's something that I think might be worthwhile. Right now, people are working on origin authentication, which is a database that's just going to map IP addresses to their owners, right? If you had such a database, so if we were living in the world of this database, actually giving the providers this list is not that hard because it's in the database, right? So now providers know the IP prefixes that their customers are supposed to have because this database actually works properly and has this information, right? So all of the work that we're doing on origin authentication actually is going to help as well with defensive filtering. Okay, so that's, I think, at least one positive thing that I can say from this work is that people are trying to do this. And so once we have this done, we actually can give providers the ability to filter their stubs. Now all we have to do is actually expect them to do it, which is sort of another altruistic thing that they would have to do, but at least getting the list is not so hard like it is today. Okay, yeah.
This idea of a database is dangerous because it could be attacked too, and then everything is off.
Okay, yeah.
Wouldn't it be better to come up with a protocol of interaction between the various BGPs so that you can trust this protocol more?
Yeah, and actually that's why people sort of talk about, so Steve should probably be the one to answer this. But the question is, so when I talk about a database, at least for the purpose of this research, I'm just looking at functionality of like security functionality, and so the database gives me the functionality I want. When you actually go to implement this, you probably don't want to have just a single database, right? You probably want much more robust infrastructure to do that, right? So that's something that people are working on. I mean, Steve, do you want to tell a bit more about that?
There is the SIDR work, there's this RPKI tree. There are a lot of reasons for wanting a PKI that describes address, prefix ownership, including just administrative dealings with the RIRs. And yeah, we all realize that this is a really good thing to use for implementing defensive filtering with minimal overhead. It's been tried in the past with the RADB, and that gets indifferently maintained. Here is something that needs to exist for other reasons, and therefore is much more likely to be up to date.
That's another question. Your measure of success of attacker is how much messages can get through.
Yeah.
But I suspect the attacker may want to have a specific message.
Yeah.
They don't care about how much, they care
Yeah.
to get this bank.
Yeah, I agree.
Do you have any?
Not in this data, but that could be done. So we have a framework that would be able to say if the attacker wanted to attract this particular set of customers, then he can get them. The reason I didn't evaluate that is because I don't know what a particular attacker would want to attract. I mean, something that I could possibly try doing is saying, you know, convincing the major networks to route through him, or convincing certain content providers to route through him, or something like that. But we didn't run that here. But you could do that. So the reason we just did it this way, we were just looking aggregate, having every AS be equal, which perhaps is not the right thing to do because each AS doesn't give you the same amount of traffic, right? So there are like more elaborate evaluations you could run. Yeah. Is there a question here?
Going to follow up on what Steve was saying. One of the proposals that has gone into CIDR is actually adding certificate information to the RPSL. So if the RIRs actually put the entries into the RADB signed as they assign a prefix to an AS, then that information would be much more up to date. So now you have a distributed database with that mapping that would allow you to check the origin information for all those prefixes.
Yeah, precisely.
Yeah, so basically, I mean, the nice thing is that what we're showing is that defensive filtering is pretty useful, and that all the security steps we're taking to implement things like secure PGP, which is path validation, will also let us do things like filtering properly. And filtering is really almost as important as path validation. That's what this work is showing. Yep. Okay.
Something about your simulation methodology.
Yeah.
Did you statically use paths, or did you use some kind of existing simulation?
Oh, okay. Yeah, we wrote. Yeah. So the actual evaluation methodology. So what we had was So the question was, how do we do the evaluation? How do we do the simulations? I have the graph of what the internet looks like with the business relationships. I'm going to run an algorithmic simulation based on breadth first search, where nodes are basically just choosing their paths using the rules that I gave.
Okay.
So prefer customer, prefer peer, and then prefer provider.
And one other question.
Yeah.
In terms of trying out different strategies, you know how you said that there's this smart strategy and then there are others.
Yeah.
Did you have some base of policy primitives that you would then apply to that algorithmic analysis of paths? Like, is there some like set of things where you said some combination of these 5 things, you know, announce?
Yeah. So okay. So
I don't know if I'm being very clear.
yeah, I think. Okay, so let me restate the question. What kind of strategies can the attacker do that might be better than my smart attack strategy? Is that?
Or do you have some enumeration built into your analysis of what those kinds of things are?
So not in the simulations. So the simulations were just for the smart attack strategy. But here are some examples of what smarter attack strategies might be. How much time do I have? We're over time. Okay, so I want to show you one example, VJ, so you can get an idea of things that can happen. This is really cool. I kind of want to show this anyway. But showed before was announcing longer paths is better than announcing shorter paths, right? So when you haven't, so one possible strategy beyond the simple one we evaluated is, you have many, many paths that you can choose from announcing. Just try announcing each one of them and see how effective that is. And that would have actually been enough to get the example that I was talking for most of the talk, get him to get his best traffic attraction, right? Here's another thing that you can do, okay? Here's our network that wants to attract traffic. These are customer paths, right? We get to Sprint. Sprint has sort of a peer path here and a customer path there. Customer path is preferred, right? I'm just going to build up the routing here. XO Communications has a customer path and a peer path. So the customer path is preferred because it makes money. TeliaNet and Cogent, which are both tier 1s, who may have different names today, I'm not sure, have 2 paths here. This is a peer path through AT&T, and this is a customer path through XO Communications. So they're going to prefer the customer path, right? And when you run the simulations, AT&T gets 40% of the traffic. Okay, so this is the destination. Basically, 60% is going here and 40% is going there. Okay, so let's suppose AT&T wants to do better. What he's going to end up doing is he's just going to block this edge. He doesn't want to announce anything to XO Communications. So XO Communication has now no choice to go through AT&T. He's got to go through Sprint. And now the question is he going to announce paths to TeliaNet and Cogent? And the answer is going to be no, right? Because these guys are his providers, and this is his peer. So he has no reason to carry traffic like this because he's not going to be making any money. Okay, does that make sense? Neither one of these is a customer of XO Communications, and so XO Communications is not going to announce these paths. Okay, so these paths get blocked. TeliaNet now has only the choice of peer paths, so they're going to route through peer paths, and AT&T gets 10% more traffic. Okay, and the reason for that is because it announced to less neighbors. By announcing to less neighbors, these two guys are using 3 hop paths instead of 4 hop paths. More traffic is going through them and ending up going through AT&T. Okay, so another strategy that you can evaluate is sort of try announcing to different subsets of your neighbors. And if you don't have too many neighbors, then you would actually be able to run through all those strategies. Right? We didn't do that, but we could have.
And
right?
You don't have some immediate way of plugging those changes into your...
No, I do. I totally do. I totally do. When I ran the large-scale simulations, I didn't do it. Yeah, but the thing is, so this type of thing is actually, you could probably evaluate this pretty easily because lots of nodes have low degree. Some nodes have very high degree, but for the low degree nodes, you could probably run through all the strategies. We didn't actually do that, but we could have done that. Yeah, so that's another example of a heuristic you could look at. Okay. All right, so I'm going to stop. Thank you.